All right, y'all. So I was asked to create a solution for this problem right here, which was from our week 9, day 1 classwork. This is off of slide 4, if I recall correctly, and it's number 3. Problem number 3 off of slide 4. Yes. Now, something that's interesting is that this problem here is going to use both exponents. It's going to use the laws of exponents and the laws of logarithms. And something else that's interesting about this problem is that it looks extremely similar to this one here, and this one, 2 to the x times 4 to the y times 8 to the z. This was from slide 3, problem number 3, I believe. Slide 3, problem 3, yeah. So if you could do this problem here from slide 3, problem 3, then you can do this problem here definitely, all right? It's just going to involve a little bit of log rules as an additional step. So I'm going to start with this one here actually to get ourselves started. Something that I want y'all to notice is that our bases here, the bases of these exponentials are all different, right? I have 2, I have 4, and I have 8. Because my bases are all different, I cannot use my rules of exponents, right? Because notice that my multiplication rule, which is the one I'm kind of wanting to use, right? You can see they're multiplying. So I kind of, in order to combine these, I want to use the multiplication rule. But the multiplication rule, you have base A, base A. The base is supposed to be the same, right? Because it results in that exact same base. The idea of these rules of exponents is that they have to do with when you have the same base, right? So what can I do to these terms in order to get them to all have the same base? Well, something interesting to notice is that actually every single one of these terms, they have something very similar in common. They are all powers of 2, all right? A lot of people, if I ask them what these have in common, a lot of people told me that they're all even, and that is true, they're all even, but specifically even more important than that, these are all base 2. This is 2 to the power 1, 2 to the power 2, and 2 to the power 3. This is going to be a really common trick when you are working with exponential form, all right? So what I'm going to do is I'm going to use these powers of 2 to replace the bases of each term in order to get them to all be some exponential of base 2, okay? So let's see what that looks like. So 2 to the x can stay as is. We have 2 to the x times 4 to the y. I'm going to turn 4 into 2 squared. And so now I have 2 squared to the power of y. And finally, I have 8, which is going to be 2 cubed. And that's raised to the power of z. So I haven't done anything too crazy yet. But this idea is kind of the trick of this problem. Once you think of this and realize this, it actually all just comes into play pretty nicely. We're going to use the power of a power rule right here. Oops, let me highlight that. The power of a power rule, which tells us that if I have an exponent on another exponent, then they multiply. So 2 squared to the y is going to be 2 to the 2y. 2 cubed to the z is going to be 2 to the 3z. And 2 to the x is still 2 to the x. Now that I have exponentials that are all of the same base, right, base 2, I can actually use my multiplication rule. And when I have exponentials with the same base multiplying, their exponents can add. So this ends up being 2 to the x plus 2y plus 3z, right? So that was the solution to that problem. Now let's look at our original question, the one with the natural logs. We're going to use the exact same idea. We have 2 to the natural log of x, 4 to the natural log of y, 8 to the natural log of z. So I'm going to rewrite 4 instead as 2 squared. And I know that if I have 2 squared being raised to the natural log of y, then those will multiply, right? I'm essentially I can skip to this step right here. I can pretty much just skip to this step. And instead of having x, y, and z, I'm going to have ln x, ln y, ln z, from the exact same reason as how I got it here. So I have 2 to the ln of x times 2 to the 2 ln y times 2 to the 3 ln z. To be honest, I could have just skipped this one, huh? So when you have a bunch of exponentials multiplying each other, the multiplication rule tells us that their powers will add. So this would end up becoming 2 to the power of natural log x plus 2 natural log y. That's not a y. Y plus 3 natural log z. Now, there is a little bit more to do, and what we're going to do is we're going to actually dive into this piece here, all these three of these logs adding each other. Because from our laws of logarithms, we actually have something called the product rule. The product rule tells us that if I have two logarithms adding each other, they can combine by multiplying the insides. One issue with the power rule, though, notice that these logs have no coefficients. There's nothing in front of the log. In order to use the power rule or the quotient rule, I need to have logarithms with no coefficient, but these guys do have coefficients. See the 2 in front and the 3 in front? Those are coefficients. So how do I get rid of coefficients? We use the power rule, right? See, there's this cool thing where with a logarithm, if there's a power inside of my logarithm, I can bring it to the front of the log, right? So if I have log of x to the y, that's going to be the same thing as y times log x. So that's an interesting adaptation there. Yeah, this example is kind of bad. It should say, instead of 8, there should be a middle step saying, oh, well, 8 is 2 to the third. And so notice the 3 goes in front and becomes 3 times natural log of 2. So we're going to actually use that here, but in reverse. I'm going to bring the 2 into the power of y. I'm going to bring the 3 to the power of z. So that gives me 2 to the power of ln x plus ln y squared plus ln z cubed. Now I can use that product rule where all these logs adding will multiply their insides. So I get 2 to the natural log of x y squared z cubed. And that is the simplified form of this expression. Yeah, this one's a bit challenging, definitely. It uses a lot of ideas, but I liked the idea of kind of expanding upon this problem here from slide 3 in slide 4 by just adding another layer of intricacy. I feel like if you can do problems like these, like this one, then you can do anything, right? It uses so many of the rules. It used 4 of them: the multiplication for exponents, power of power, the product rule for logs, and the power rule for logs. Crazy, isn't it?